Right, welcome back. Hopefully you had a nice break. Right, we're going to carry on working through this then. So, okay, so we got up to question 4. A student titrates, so titration, the method of calculating the concentration of an unknown. All right, so they are titrating sodium hydroxide, this here, against sulfuric acid. Pay careful attention to this 2-to-1 ratio here. The student titrated against 25 centimetres cubed of the sulfuric acid of an unknown concentration. So what that's saying is the sulfuric acid, we know its volume is 25 centimetres cubed, but we don't know its concentration. And now the sodium hydroxide, we do know its concentration and we do know its volume. You're given its volume down here, except you're given 3 values for its volume because the titration has been repeated multiple times. And actually in the first part, what we've got to do is calculate the mean volume of sodium hydroxide used. So titer is just the volume that was titrated. Okay. Now, when we're calculating the mean from a series of data via titration, it's very important that you only calculate the mean of concordant values. And to be concordant, so that's concordant, okay, to be concordant means within 0.1 centimetres cubed of each other. Okay, so if you're within 0.1 centimetres cubed of each other, then you are concordant and they can be included in the mean. So we've got 12.4, 12.5, they are concordant, and then we've got 15.80. Now that 15.80 straight away, I don't know if I have a strike through on this. Tell you what I'm going to do, delete, okay, because it's not concordant, all right, it's not concordant. So I've got to do the average of those two. So 12.40 plus 12.50. Okay, I'm going to do that sum, divide them both by 2, okay, and that should give me 12.45 centimetres cubed, okay. So my mean titer there should be 12.45 centimetres cubed. Don't know what I'm doing with my screen now, there we go. Right, so there's your answer. Okay, now how do you get the marks on this one? You get the first mark for excluding that anomaly that we removed, okay, so that non-concordant value, and then you get your second mark for getting the value of 12.45 there. Okay, use your mean titer and the information given to calculate the concentration of sulfuric acid. And what I'm going to do, just to make this a bit clearer, is copy and paste this. Okay, pop that there. Okay, because what we need to do for every single one of these is we need to know about its, we need to use the titration equation, which is N equals CV. Okay, N equals C times V. N is the number of moles, C is the concentration in moles per cubic decimetre, and V is the volume in decimetres cubed. Okay, remember to get a volume in decimetres cubed, you do need to divide by 1,000. Okay, so I'm going to just write along the edges here, N equals C equals, and V equals. And we'll see what values we know. So the sodium hydroxide, I do know its concentration. It's written all over the place. Look, using 0.100 moles per decimetre cubed. See that there? Moles per decimetre cubed. There's the units of concentration. So we've got 0.1 for the sodium hydroxide's concentration. It's also written here, and it's also written here. So you definitely should know its concentration as 0.100. Okay. Now its volume is that mean titer that we just calculated, with the exception that we've got to divide that by 1,000 on the basis that that's in centimetres cubed. So I'm just going to show a little bit of working down below. So we're going to do 12.45 divided by 1,000. That should give you 0.01245 decimetres cubed. I'm just going to double check. Yeah, I think that's right. There we go. Okay, so 0.01245 decimetres cubed. Remember, centimetres cubed over 1,000 is decimetres cubed. Okay, so there is my volume. Okay, so now what I've got to do is work out the number of moles of this sodium hydroxide. And remember that my equation is N equals C times V. So if I multiply C, this concentration, by V, this volume, I should get the number of moles. So again, I'll just show my working down below. 0.100 times 0.01245, and well, that's basically a tenth of it, isn't it? So 0.00125. Okay, so there is my number of moles, 0.00125. Okay, now the mole row is the only row that follows the stoichiometry, that means ratio of the equation. And if we look at the number of moles of sodium hydroxide, then they are going to be 2 times whatever the moles of sulfuric acid is, because there's an imaginary 1 here because no number's been written. So what I need to do is divide this value here by the number in this column and then times by the number in this column, and I'll get the number of moles of sulfuric acid. So what I need to do is divide this by 2 times by 1, so that's the same as dividing it by 2. So I'm going to take this value next, show my working, 0.00125 divided by 2 equals okay. Right, now I've got 6.225 times 10 to the minus 4 moles. Okay, so there's my number of moles now of the sulfuric acid. It's half that of the moles of sodium hydroxide. Okay, now I'm going to see if I know any of these other values. Do I know concentration? Do I know volume for the sulfuric acid? Well, it says here the concentration is unknown. And that's actually what we're trying to work out, right? Calculate the concentration of sulfuric acid. So what I'm going to do is just over here, I'm going to put a little question mark because that's what we're trying to work out. That's the aim of this entire question. Now the volume of that sulfuric acid, let's see if we've got it anywhere else in the question. Here we go, 25 centimetres cubed of sulfuric acid. But remember, that's got to be in decimetres cubed, so I've got to divide it by 1,000. So 25 divided by 1,000 equals 0.025 decimetres cubed. Control dot. Yeah, there we go. Okay, so I've got 0.025 here. So now what I've got to do is work out C. Well, if my original equation is constant N equals CV, then C will equal N divided by V. So what I need to do now is divide this number by the volume, and I should get the concentration. Okay, so I'm going to take the number of moles and I'm going to divide that by this volume. Okay, so I'm just doing that now on my calculator. There we go. And I got the answer, and hopefully so did you, of 0.0249. Oh, 249, there we are. Okay, so that number there is this number here, that concentration. Okay, oh, I didn't copy it, did I? There we go, 0.0249. Right, because it's a concentration, we do need to give units for this. And if we look earlier to what the units for concentration were, they were moles per decimetre cubed. So I'm going to include that same unit there for the concentration. Okay, so just to recap, we wrote in what we knew about each in terms of N, C and V. Then we calculated the number of moles of the sodium hydroxide using our mean titer. We then divided by 2 to get the number of moles of sulfuric acid, and then we divided moles by vols. Moles over vols equals concentration, and we've got our concentration there. Okay? Right. Why would we place the conical flask on a white tile during the titration? Well, you've got to put an indicator into the conical flask, and depending on whatever surface you're working on, the background's going to have a different colour. So we've got to make sure that we put it on a white tile because it allows us to see the colour change of the indicator at the end point. Remember, the end point is when the indicator changes from one colour to another. Now, you're not going to use something like universal indicator because that doesn't have a clear colour change. But if you use something like phenolphthalein, then that turns pink when it's alkaline, so it turns pink at the end point. You need a white tile in the background so you can clearly see the colour change at the end point. The end point is how they would have judged these volumes here, right? So they would have stopped adding sodium hydroxide when that colour change occurred. But unless you can see that colour change really, really clearly, then you're not going to really know when that end point is. So putting it on a white tile enables you to see that colour change more clearly at the end point. Okay, question 5 now. A student was investigating whether a series of reactions were endothermic or exothermic. Okay, and here's what they've done. So they've measured 10 centimetres cubed of a liquid reactant using a measuring cylinder. They've transferred it to a beaker and recorded the starting temperature using a thermometer. Nice naming of equipment here, that seems good. They've weighed 1 gram of the solid reactant using a balance, again, naming the equipment, transferred the solid to the beaker and record the final temperature using a thermometer. Suggest 2 improvements. Right, improvement number 1, I would never do this reaction in a beaker. I would always do this reaction in a polystyrene cup. If you're going to measure a temperature change, then you don't want any external heat getting in and you don't want any internal heat escaping, okay? So we need to insulate it using a polystyrene cup. So I'm going to use a polystyrene cup instead. Might want to stand it in a beaker so it doesn't fall over, but certainly use a polystyrene cup instead to insulate to prevent heat escaping or entering. Because otherwise that temperature reading that you record is going to be different. Right, also, it says here they've transferred the solid just straight to the beaker and then just recorded the final temperature. I don't think if you transfer the solid to the beaker, you're going to get an instant reaction. And actually, I think you're going to need to help that solid react a little bit. So my second improvement would actually be to stir the reaction mixture. Stirring is so important because it ensures the reaction goes to completion. Unless you stir, the reaction won't go to completion, and that's actually why chemical engineers always have to design reaction vessels on a large scale with rotary blades inside which ensure adequate mixing. Okay, let's move this question down. Right, so the student's results are shown in the table below. Complete the table. So you've got to work out the temperature change. Now the way you do this is you take the final temperature and you take away the starting temperature. So 16.5 minus 21. That's going to get you minus 4.5 as your answer for that one. I would have accepted 4.5, but the key thing is to notice is that this is a decrease in temperature, which means that the reaction must have absorbed some of the heat energy that was already there, so the surroundings have cooled down. That's a clear indicator of an endothermic reaction. Okay, this one here is increased by 6.5. Okay, so that means it's released its heat energy to the surroundings, so that's exothermic. Okay. And this one's gone down to minus 38, okay? Apologies, this is pretty easy, but when you're sitting in front of the computer, you don't want to get it wrong, so take me a second. Right, so 21 minus 38, you should have got minus 17 there. Oh, no, I misread the question. Sorry, guys. Right, here we go. The starting temperature was 21. The final temperature was something. Oh yeah, no, that is totally right. Yeah, it was minus 17. Sorry about that. Okay, yeah. So the temperature change was minus 38. So if it went down by 38, then it must have been minus 17 at the end. So that's endothermic. Okay. I would normally stop and re-record right now, but I'm just trying to do this in one take. Right. Okay. Complete the fully labelled reaction profile. Right. I want to show you a little trick here. Okay. So if you're trying to add images to these sorts of documents, it's really easy. You click Insert. And you go to Drawing and you click New, and you can do a little drawing in this box here, which is well handy. Now I'm just going to escape this quick. I'm just going to save and close as if it was there. So we've got energy and course of reaction. So I want to correct that. I'm going to see if I can actually copy and paste that into the drawing tool. Let's have a look. So Insert, Drawing, New. Here we go. Oh, look at that. I can actually copy and paste what's there into the drawing tool and modify it. That's really cool. I used Control C for that. Right, so it's for, oh no, what was it for? Was it endo or exo? I'm going to have to save and close that. What's happened? Oh dear. Okay, it was endothermic, just to be clear. It's endothermic. Okay, right, let's delete that. Okay, so I'm going to copy that, Control C, Insert, Drawing, New. Let's paste that on. Right, let's zoom in a little bit. Maybe I overdid the zoom. Here we go. Right, cool. So endothermic absorbs heat energy. So I'm going to put a line here for the reactants, and then I'm going to put a line up nice and higher for the products. Okay, I'm just going to exaggerate that a little bit. Okay, so we're going to call this level here our reactants. Always on the left, the reactants. Okay, there we go, and copy and paste that. There we go. Take that over there. That's going to be my products over here. Okay, products. There we go. Okay, right, so it's absorbed energy, so we need to show that. So the way I'm going to show that it's absorbed energy is using an arrow, and that arrow always goes from reactants to products. Okay, it needs to be pretty much exact. So that's my energy transfer. Energy transfer, and that is absorbed. Okay, that's absorbed. It's a bit difficult to select exactly what you're trying to point out on this thing. There we go. Right, but as you hopefully know, it doesn't just take this pathway where it just kind of like jumps straight up. It does actually take a curved pathway. So try and add a curve. Let's see how this works. Okay, a bit dodgy. Let's delete that. Try again. You double click when you've reached the end of the curve with this, by the way. So I'm going to go start here. Can it kind of go across a little bit? Like there we go. That's all right. That would do. Double click. There we are. Okay, so I've got a curve. It's a bit naff. I need to add my activation energy onto that now. So I'm going to add an arrow. Show it going up. Right, it's got to touch the peak. Apologies, this is rubbish. Tell you what I'm going to do. I'm going to move my energy transfer out the way quickly. Here we go. Energy transfer. As long as it's starting at the level of reactants and going up to the products, that's fine. Activation energy's always got to start at the reactants and touch the peak. Okay, R to P. All right, so that there is my activation energy. Okay. Right, so now, ooh, that's not the best. There we go. Look, it's clear enough, right? That arrow there, that arrow there is the activation energy. That arrow there is the energy transfer. If I click save and close, boom, delete the old one. There you go. I've modified the diagram that's there and published it in there. You can do that as a handy little trick. Copy and paste what's there, put it into the drawing tool, draw over the top of it. Lovely. Okay, right. Next up, I'm going to move this one down so we've got enough room to work on it. Okay. Using the values supplied, calculate the overall energy change for the combustion of propane. So I've got to look at what bonds are in these reactants and break those, and then look at what bonds are in those products and make those. Okay, so I'm going to start off with a little bit of bond breaking. Okay, you can see my mouse hopefully. So I'm looking at this propane to start with, and I can see two of these CC bonds. Okay, so there's C to C there and there's C to C there. So I've got to break 2 times C to C, which is the same as doing 2 times, let's have a look in our table here, 348. So 2 times 348, that's going to equal 2 times 348 is going to be 696 for that one. Okay, so I've broken those C to C bonds. Next up, I'm looking at these CH bonds. I'm seeing 1 here, 2, 3, 4, 5, 6, 7, 8. Okay, so I've got 8 times that C to H bond, which is the same as doing 8 times. C to H is there at 412. Okay, and that is 8 times 412 is 3,296. Okay, so that's that first molecule done, but we've got to do everything on the left hand side of this arrow. So now I've got 5 of these O to O double bonds. Now because they're a double bond, you don't need to double them, you just need to use the correct value for the double bond in the table, which is this one here. Okay, so we've got 5 because there's a 5 in front of it. Remember, you've got to use those balancing numbers in front of it. 5 times O to O, that's a 0, O to O. Okay, so that's 5 times this 497 value here. Okay, let's change that to a lowercase. Right, so 5 times 497 equals 2,485. Okay, that looks like all the bonds on the left now, so I'm going to add these values up. So I'm going to do 696 plus 3,296 plus 2,485, and I'm going to add all those up, and I'm going to get this total equals, right, let's do this. Hopefully I've got this right on the first take. Right, 6,477, and the units for that are kilojoules. Oh, lowercase k, caps lock on, there we go. Right, so there is my total for the bond breaking. Okay, you've got a mark for that. All right, so there's a total for the bond breaking. Right, now what we've got to do is the bond making. So we're focusing here on the products. Okay, so let's have a look at what bonds I've got. Right, I can see this C to O double bond is occurring twice in a single molecule of carbon dioxide. So I've got C to O and C to O, but then everything in this molecule is multiplied by the 3 here. So I've actually got 6 times the C to O. Yeah, so 2 C to O's per molecule, but then 3 molecules. So that's going to be 6 times C to O, which is the same as 6 times our value here of 803. Okay, so 6 times 803 gives me 4,818. Okay, right, next up, bring this across. If I look at a single molecule of water, so this molecule here, I can see that it's got this O to H bond twice per molecule. Okay, so this O to H at 464 is twice per molecule. But I've got here 4 molecules of it. So 4 times 2 per molecule is actually 8. Okay, so we're going to have 8 times O to H. Okay, which is the same as 8 times 464. Okay, so that's 8 times 464, 3,712. Okay, that looks like all the bonds now in my products. Okay, so I'm going to do my total, and then I'm going to add them up. So my total for this, okay, I've got to add that to that. $8,530 kilojoules, lowercase k, capital J. Okay, so there's my bond breaking, there's my bond making. Now all we've got to do to work out this overall energy change is do bond breaking minus bond making. I always call it left minus right, that's the way I remember it a little bit easier. So we're going to do overall energy change equals bond breaking minus bond making. So that is the same as doing 6,477 minus 8,530. So I'm going to get here minus, that's important, 2,053 kilojoules. Because that's a negative number, okay, it means energy's been released. It's the same as a downwards arrow on a reaction profile. So that's energy released. Okay. Right, so explain how your calculation shows that this is exothermic. Well, one of the things you need to know about bond breaking is this is energy absorbed. Bond breaking, you've got to put energy in, okay? Whereas bond making actually releases energy, okay? Bond making releases energy. So if you look at the two numbers here, we've put in 6,477 kilojoules of energy during bond breaking to break the bonds. But we've released 8,530. So overall, more energy has been released during this bond making than was ever put in during bond breaking. So that's how we're going to word this one. Overall, more energy is released during bond making than was, you could say absorbed, or put in, absorbed during bond breaking. So more energy was released during bond making, that was that 8,530, than was absorbed during bond breaking, that's 6,477. Okay? Right, get this one down. Okay, next question is about cells and batteries. Name the two components of a cell. Every cell needs a liquid with free moving ions called the electrolyte, and it needs some metal rods that we call electrodes. Why is the liquid found within a cell able to conduct electricity? The liquid found within the cell is this electrolyte stuff here, okay? And the electrolyte has free moving ions, okay, because it's a molten or dissolved. Well, it's going to be dissolved, isn't it? It's not going to be a molten battery. That'd be horrendous, okay, because it's a dissolved ionic compound. All right, you don't need to write that, but it's got free moving ions, which are free to move and carry charge. Free to carry charge. Okay, so your ions can move freely in the electrolyte and carry charge. Next up, a student wants to make a 6-volt battery using 1.5 volt cells. Explain how they could achieve this. Well, when we want to create a battery, what we've got to do is connect individual cells in series, okay? And we need to connect enough of those cells such that their individual voltages add up to give 6 volts. So to make 6 volts, well, I need to know how many cells I've got to connect up. So 6 divided by the individual cells of 1.5, that should give you 4 cells, okay? So this means we need to connect 4 cells, okay? So that's the first point, or 4 of the 1.5 volt cells in series, okay? So you get the first mark for saying you've got to connect 4 of them up, and then the second mark for saying that you're going to do it in series. Okay, we've got the current output of a non-rechargeable cell over time. This looks like the world's worst cell because it's gone flat within 180 milliseconds and it's only outputting a tiny current there in milliamps in the first place. The only reason I've given you this graph is I couldn't find a tool that copied it across very easily from Excel into Google Sheets. So yeah, it's just a poor graph, but you get the idea. It's going flat, okay? Now, we've got to explain why it's going flat over time. It's probably a capacitor, this, to be fair, actually, which is a type of cell. It's discharging as the reactants get used up. This is 3 marks, okay? So it's discharging as the reactants get used up. So that's the first point. We need to say the reactants are getting used up. Then we can say that as it discharges, current decreases. And then finally, we could argue when it's first gone flat. Now, actually, looking at when that line is on the baseline there, I was wrong. It's not 180 seconds. I think it first goes flat at 170 milliseconds. Okay, so it's flat by 170 milliseconds. So reactants get used up is the main thing I really wanted to get at with regards to it being a non-rechargeable cell. But then obviously there's some interpretation of the shape of the graph there as well. Why is it possible to recharge some cells? Well, they contain a reversible reaction. Okay, so if the reaction is reversible, okay, then products can be turned back into reactants by the application of an external electrical current. Okay, so reversible there is key, a reversible reaction for a rechargeable cell. Products turning back into reactants, and the way we achieve this is by applying an external electrical current to the battery or cell. How are fuel cells different to conventional cells? We had this in our lesson last week. So fuel cells require a continuous supply of fuel and oxygen, and that fuel is likely to be hydrogen. And I think we are done. Woohoo. Right, thanks for bearing with me there. Apologies if there's any errors in the video. I did notice in the first video I made one error. I did watch it back. It was on the question, let me just show you where that error was made quickly, on alkalis and naming the insoluble bases. Let me just get back to this. And here. Right, I just want to make really, really clear. An alkali is a base that can dissolve in water. An insoluble base is a base that can't dissolve in water. Just want to make that one really clear. Okay, thanks for watching, guys. Have a look at the work for next week. There's a video up there of the work. I hope it all makes sense. I've also got some videos of me doing the practicals to help you understand that a little bit more. Keep working hard. Cheers.